Okay, so hopefully we agree on the mathematical derivation that this is the correct way to update our policy. Next, I'm going to try to give you at least some intuition for why this is probably the correct way to go. So let's see what actually happens if we follow this gradient step. Each increment in our probability of taking a specific action is proportional to the product of a return, that's the GT, right? And a vector, right? The vector that is defined by our gradient. The gradient of the probability of taking the action, so the vector, the gradient, is the probability of taking the action actually taken over the current probability of taking that action. Okay, so this will be the update direction, the vector here. And this vector is the direction in parameter space, theta space, that most increases the probability of repeating the action AT, the one that was actually taken, in future visit to state ST. Right, so this tells us how to increase the probability of taking the action that was taken, and we multiply that by the return. So if we'll have high return, we'll increase it by more. If we'll have low return, by less. And indeed, the update increases the parameter vector proportional to the return, proportional to the GT, and inversely proportional to the action probability. Why is that important? So, proportional to the return, that makes sense because it causes the parameter to move most in the direction that favor actions that yield the highest return, right? You have higher return, higher GT value, then you want to increase the probability of taking that action in a stronger way. But why is it inversely proportional to the probability of the current probability of taking that action? That makes sense because otherwise actions that are selected frequently, maybe your current policy is wrong. So you don't want to always increase the probability of taking actions that you're current. You don't want to be overcommitted to your current policy if it's a wrong policy, right? Because that might mean that actions that are selected frequently are at an advantage. The updates will be more often in their direction. And they might win out even if they do not yield the highest return. Okay? So this is important in order to help us avoid actions that might be frequent under our current policy but are still not the best actions to take. So reinforce, as the basic reinforce algorithm uses GT, the observed return, in its basic form. In this sense, reinforce is a Monte Carlo algorithm, right? It's well defined over episodic cases, for the episodic case, with all updates made at retrospect after the episode is complete. So we'll have to complete a full episode, then we'll be able to compute all of the GTs for all of the time steps, and we'll be able to do the policy update for each time step in hindsight. And by the way, I know this is kind of a disadvantage when we said no, we usually want to perform online updates at each time step to apply all of our computational efforts per time step to divide the computational effort over the time steps, and also we don't want to be restricted to only perform episodic updates. We also want to be able to perform online optimization over continual problems. So, but the basic reinforce algorithm is an episodic algorithm. Later on we're going to see some more advanced versions. So indeed this is the reinforce algorithm, the basic one, and as you can see it does not require, although the math might be a bit complicated as we've seen before, the algorithm itself is actually pretty simple. you complete an episode, and then for each step in your episode, you compute the g, the return from that step, and then you perform a gradient descent step. And so this is the pseudocode. Any questions?
Why is there a logarithm used in the update over here?
Yeah, right. That's a good question. So the policy gradient theorem, or the policy update that we derived, seems to be a bit different than the one presented in the pseudocode, right? So we said that the update should be g time gradient of the policy over the policy, and not the natural logarithm of the policy. Well, actually, it's exactly the same, right? Actually, the natural logarithm of the policy, the gradient of the natural logarithm of the policy, is exactly the same as the gradient of the policy over its own value, over its current value. Right, so if you remember correctly, the definition of a natural logarithm, the gradient of a natural logarithm is the gradient of the function inside the natural logarithm over the function, the current value of the function. So this is actually the same thing. However, actually, in the literature you might see even other instances of the policy gradient updates. Actually, in many cases, it's actually pretty common to represent this update rule as gradient of the log of the policy. So instead of the natural logarithm, you'll see this most in many papers. So you'll even see log here, log of the policy, and many people will actually define it as grad log pi, or actually say it this way. And again, that's not a problem. It's not, so the gradient of the natural logarithm is not the same, is not equal to the gradient of any other logarithm, but it is proportional to it, right? And again, you can see this in your derivative table definition, where the gradient of the natural logarithm equals the gradient of any other logarithm multiplied by the natural logarithm of the basis of the other logarithm, which is a constant. That is, they are equal in proportional, they are proportional to each other, and as I always say, proportional constants does not matter when we do a gradient descent step. You just, the learning rate, the alpha value just absorbs everything. You might need to just, if you use log instead of natural logarithm, and with different bases, shouldn't be a problem. You might just need to set a different alpha here. But practically, it's not an issue. Yeah, a different question?
Yes, so over here I noticed that we're using a soft policy and modifying the gradients are modifying the probability of an action. So would this also apply to deterministic policy, the same update?
No, in deterministic policies, well, maybe, depends on I'm sure you can find some unique algorithms that maybe do a unique combinations under some assumptions. Specifically in this course, we are going to cover, actually we're going to cover several actor-critique algorithms, but we're going to cover one actor-critique algorithm with deterministic policy. This will be the DDPG, the deterministic policy gradient.
Deep deterministic.
Deep deterministic policy gradient algorithm. For the algorithm that we're going to cover, no, we're going to use a different way to estimate the gradient of the policy, and not this approach. We're going to use something else. So generally in policy, the policy gradient that we defined so far is only relevant for soft policies. Okay? And here are some results on the crazy corridor problem that we've seen before. right? Where we have to converge on a stochastic policy, on a soft policy, where you see that we use the same pseudocode here, the basic reinforce algorithm, with different alpha values. And indeed, you can see that with the right step size, specifically with an alpha, a very low alpha here, but with this specific alpha, the total reward per episode approaches the optimal value of the start state, which is given here, the dotted line. Okay, so we can converge, and we can converge pretty quickly after, like, how much would you say? 800 episodes. Actually, is that quick? I don't know. This is a very simple domain. But
I don't know how many time steps is an episode. Okay, maybe 4.
Right.
Yeah, that's pretty.
Right. You might think that this.
the alpha is small.
Yeah, that's true. The alpha is very small, so it's a very slow update. And also, it's a crazy corridor, so it might actually be hard to learn. But you might think, okay, yeah, it's a simple problem. We might expect to learn faster. And indeed, this is a very simple algorithm. Later on, we'll see a lot of further enhancements to this algorithm, which actually allows us to learn much quicker, to be more sample efficient. In any case, the simple variant, the Monte Carlo variant of the reinforced algorithm, is guaranteed to converge to a local optimum under standard stochastic approximation conditions for decaying the learning rate, as we previously discussed.